what can we do? You know, how we actually do computation with these quantum bits? Yeah, there's two types of quantum bits, and as I said, the characteristics of quantum bits is where we actually, when we start reading the quantum bits, they fall into 0 or 1 position, but they can superimpose the quantum states. They can be multiple states at any given time. There's two types of quantum computation that we can do. One is the adiabatic, or what's called the hybrid quantum computing, that essentially works for the lowest energy, you know, looks at the system and looks at the quantum states when they fall into the lowest energy. I have a graph that actually shows this a little bit more graphically. It's easier to know. And that is known as the position that actually you have to read them. So the goal of any quantum state is to be at the lowest possible energy, and essentially the system measures the energy level, and once at the lowest energy, then it says, okay, this is the outcome, this is the measurements that you are looking for. And in this type, so it's best suited for optimization problem. And I'll discuss the use cases. But optimization problem is an example. A known example is a traveling salesman. You know, what are the best routes for a person to actually go into various stops? And one of the things that you can do, obviously, is to you can apply. There's been a lot of work to use this for sampling, for machine learning, and one of the biggest providers of this is D-Wave. D-Wave is possibly one of the best platforms that actually is around for adiabatic. Some people, they say it's the only one, but Fujitsu has claims that they also have adiabatic or hybrid quantum machine that you can use. I haven't used it, I don't know, but D-Wave actually have, and D-Wave also has a very good software stack, the Ocean. And there's a lot of work. They have done a lot of really good work, D-Wave, in expanding this form of quantum computing. And the nice thing about it is that it says hybrid because you have the adiabatic, you have the quantum processing unit, but also you have the classical computers around it that does the rest of the work. So you can actually run a full. When we do quantum computing, if you think about an application, like 90%, 95% is on a classical computing. We're talking about storage. Storage is classical computing. We're talking about data transfer, everything in networking. We can't transfer qubits. And actually in the book, there is a chapter about quantum communication where we actually use entanglement as a form. It's the only way that you can do communication. 0 and 1, we can only transfer 0 or 1. Yeah, we cannot transfer anything in between. So pretty much anything is a classical except the quantum processing unit, where we actually do the calculation. Think of a computer where the CPU is only quantum, everything else is essentially a classical computer. Then the next model essentially is like selling a car. The next model is really the gate model. The gate model is the most common form of quantum computing. Pretty much anyone else besides D-Wave and Fujitsu, what they provide is gate model, where you actually do logic gates, like what we do for classical computers. And in that we have a measurement gate, where actually it is a dedicated gate that actually measures the state of quantum, and that becomes very key in reading out. So any quantum circuit that you design, at the end it needs a measurement gate to actually see what's the outcome, right? And calculations are done by quantum states, the gates, like what I said. And actually in the book, there's a dedicated chapter on quantum gates and various forms of gates and how they function, essentially how they work with the data. And there's multiple gates. You may hear, I said measurement gate, which is very important. The H gate, which is the Hadamard gate, is very important in quantum gates, which is kind of a CNOT type in classical computing. These are very important, essentially, aspects of the and when in machine learning, there's a lot of conversation how these gates actually makes a difference in the gate model of machine learning. And provides a significant capabilities, right? So there's quite a few of the quantum algorithms that we have. They run on quantum gates model, like Shor algorithm, like and the factor algorithm, like the Simon algorithm. These are big algorithms that they run on quantum gates, and quantum Fourier transform is actually runs on gate model, which does a lot of very interesting work. And one of the things, like for instance, for factoring algorithm from Shor, it's expected that quantum computers can break down SSA security encryption, which will make a huge difference in just the security domain. If you can, right now, most encryption keys that use is 1028 size, and which takes, if with classical computing, if you want to brute force this, it takes like some 100 years. But with quantum computing, can be down to a few hours. Theoretically, it can be done using Shor algorithm. It's not been
So David, just a quick question. Do you have, is it just a single slide or do you have other slides?
On what?
I don't know, because you said you're using a different monitor. Do you have a deck, or is it just this specific slide? Okay, now we can see it.
No, so this is one, and I'm going to the next one.
Awesome. Okay.
Yeah, so let me so you can see the full screen where it says types of quantum computers.
Yeah, we can see your mouse cursor too, which is good.
Okay, can you see this now, the blue one?
Right, yeah.
Okay, cool. Yeah, so essentially the quantum annealers, where we said the lowest energy state is calculated, and using the annealing of the qubit circuit. Again, as I said, the biggest provider is right now D-Wave. Fujitsu has claims, and the only service right now that actually, public service that actually is combining really good platform to get started is really AWS's Bracket, that you can have D-Wave. It's got API integrated with D-Wave, and also API integrated with IonQ and Rigetti. So you get gate and annealing, and you can actually combine them. So this is really helpful because you have a single API. You can, one of the things that is best practices with, and I'll talk about this later, is to run your application in multiple platforms, because you have to make sure you get the same result. And IBM, I would say, has my experience as the best platform in gate model, really, really good. And I used IBM's kind of platform for some of the codes that I run, for some of the algorithms, really good in running it, in actually testing it. And you can test it on the simulation that they have, but also you can take the simulation and run it on a quantum device. And using the free tier, you have to wait in line. Sometimes it can be a few hours, depending on how many people are testing. Google has really good examples. Also with the gate model, you can run quite a few of the algorithms on Google platform. Microsoft, I have not tested, but I know that they have something going. They have an offering in quantum computing, also with a very good library, the hashtag Q. And Rigetti and Intel also says that they have, and 1QBit, that I don't know why it was left out, but definitely 1QBit belongs to the gate model. Yeah. Any question on these so far, or I keep going?
You had mentioned some things as far as classical computers taking 95% of the work due to storage, networking, not being able to do that with quantum. Is that still the case? Like, I see the D-Wave stuff you have up here. I know they use hybrid quantum annealers too. Is that still the case with many of these that you have mentioned?
Yeah. I mean, so the thing is, it really doesn't make sense to do other things with, like, storage makes no sense to do it with quantum computing, right? Because it would be very expensive, and maybe not as reliable as solid state storage that we have, which is classical 0 and 1. And so if you think about a computing unit, pretty much anything that we do on a quantum application is done. A lot of different pieces is done on the classical computing, but the processing itself of the algorithms, finding the solution, that is done through quantum computing. The output goes into a classical computing. So when you actually design, I can quickly step into a slide that I have later here. Yeah, if you look at what a typical stack, an application stack, looks like, a lot of these different pieces really fall under classical computing, whereas as you see, where you actually run the algorithms on the quantum processing unit, some of the data handling can be on the processing unit, but at the end, the front end of the application, the database part is all classical computing, which makes sense. And the runtime is quantum computing, that's fine, but the essentially the data transfer back and forth between the processing, storage, database, all that is really classical computing.
Very cool. Ron, you have a question, Ron?
Yeah, hi David. On
Yeah.
your previous slide on the right, your quantum gate model, you have some gates labeled as U. I'm not familiar with what those are. And also in the middle, you have this big block that appears to be taking the output of 3 H gates. It's labeled F to the -1.
So that's so the U is the what's called, it's called some kind of an energy function, and it's in the book. Actually, I laid out what U is. It's a big equation.
Okay.
Actually, it has multiple components in it. F minus is the reverse Fourier transform.
Okay, and is that something that's been implemented? Because I've seen this in Shor's algorithm where they just kind of hand wave. There's a quantum Fourier transform going on here.
Yes, yeah. So again, this is like it's a little bit like high level, right? Just the Hadamard gate. This is the H gate. If you go in the book, has itself a quantum circuit. So there's multiple functions that go into that H gate. So a reverse Fourier transform has also it itself is like, now it's a big box, but it actually has multiple components in it. And I think it's in chapter 5 that actually describe how reverse quantum Fourier transfer actually works. And different
Are there other qubits inside of that box? Is that?
Yeah, I mean, so here this represents the qubits, right? Initial states. Typically, sure. we take a qubit and you apply Hadamard gate, and that when you H gate, and that puts the qubit in a superimposed state. Mm-hmm. That's the role of an H gate. Typically, you start with that for most of your qubits that you want to start doing some work on them, except the ones that you want to use for measurements. You want to use reference, other types of qubits. Yeah. So these on the side, yeah. And this is very high level, just a quantum gate. Just want to show how it looks like, but there's just the layout is so much. And I have actually part of the book is code snippets that you can generate these circuits, and they can be so wide and large. Actually, I couldn't put in all this in the figures of the book, but you can kind of generate that using an online platform.
So just to be clear, that F to the -1 block, is that hardware and software? Is it just software?
Hardware and software. So essentially, it itself is an algorithm. Fourier transform is an algorithm, and reverse Fourier transform is also an algorithm. And itself is you think about it as it processes some inputs, right? You get some qubits, it processes and it gives something out, and you can have it only software if you do simulation. If you do quantum simulation, that's all software. But if you can apply this on actual quantum devices, and it becomes hardware and software. Yeah. Okay. You apply it on real quantum bits. Yeah.
And so, just one last question: do you go into depth in your book as to what's going on inside that block?
Yes. There is a whole section about reverse quantum Fourier transform. Yeah, and it's a critical one. Actually, the gate quantum algorithms are classified as to 2 Fourier-based and non-Fourier-based, and that kind of how I think it's chapter 5 and 6 that actually splits, because Fourier-based and non-Fourier-based are different ones, because most of the algorithms, they use Fourier as at the end to hand it over to measurement gates. It stabilizes in a way, it stabilizes the qubit to be measured. One of the effects of Fourier transfer. And that's discussed in the book. Yeah.
Okay, great. Thank you.
Very cool. Thanks, Ron. Another thing you'd mentioned running, I think you said you ran on IBM and Google. And you say to run on multiple platforms to make sure you get the right answer. I know.
So you can, okay, go ahead. So sorry, I interrupted you.
Well, basically, I know it's probabilistic, so you have to keep running until you get a good average number. It's not deterministic like classical. So I guess what's your approach with that? Like, it's possible basically to do the same problem on IBM, Google, D-Wave?
My screen sharing kind of changed. Let me stop sharing and I reshare again. Because okay. Okay, do you see the blue screen with the
Yeah, it's
swap?
like a desktop.
Okay, now you can see the full screen, right?
Yeah,
What business problem? Okay, cool. Can you repeat the question? I'm sorry.
So basically, you said you can run on different hardware to make sure that you get the right solution. So I know it's probabilistic. So you run a bunch of times, say on specifically like an IBM, and you could do that on the other ones. So have you had good luck doing that across different platforms with the same problem?
Yeah. So one of the things that actually I recommended in most of the lab sections of the book is for the person who is implementing the lab is to repeat it, just repeat the same thing. On the simulator, you always get the same thing. You always get, I think we factor with Shore, we factor number 5 or something using Shore, which is like 0, 1 or something. And then 0, 1, 1, yeah. And then you always get the same thing. But when you go into running this on actual quantum device, even on the same platform, if you run it multiple times, you get different probabilities. That's just the nature of quantum computing. And that's why it's always better to run it multiple times on the same platform, run it on multiple types of providers. They have different quantum devices. That's why I say AWS bracket, because you can literally run your application on Rigetti and IonQ, 2 different types of qubits. You can run it on 2 different types of qubits, and you can run it on D-Wave, and then compare, and then compare it even with the classical computing. That's really the goal, to actually try to minimize the error and see where you can be closer to finding. We did a use case a couple of years ago for a drug discovery project that was exactly like this. The front end would take the formula that you wanted to see, essentially a database of millions of molecules, and try to compare that. And you could run this on multiple, essentially the backend is running it on multiple platforms. You choose, okay, I want to run it here, I want to run it there, and then you compare the outcome with each other, see which direction you go. Yeah,
very cool.
I think that should be the best method, and to really, if you're really looking for answers, especially like in the quantum finance, that's one of the things that I have in mind, is to really run the same algorithms that actually does stock trading on multiple platforms, which is very important. Yeah.
So have you developed a technique to measure quantum advantage across all these? In specific, like for classical, if something takes super long, and then for quantum, if it takes a lot shorter, like a scale to say like how much better that quantum was?
You can. You can definitely do that just to see where you can get. But the problem is, if you know the solution, you can do that easily. But the problem is to do this for an unknown thing, and then you have to make sure the answer that you're getting from the quantum computing is actually the right answer, right? That kind of becomes a key thing here, that you're actually not. And then it's a question of how much you have to run it, and then if you actually have to run it multiple times on multiple platforms to find that maybe the quantum advantage is not really that big as you thought, as of a single platform, right?
Yeah.
So you have to take into account everything that you have to do. And I mean, obviously, I mean, if you think about like just factoring, like I think I mentioned in the book, when we factor 5 with 3 qubits, it takes like, I don't know, a fraction of a second to actually do it. Now think about how long would it take if on your CPU you had only 3 bits, right? That's how you can think about the advantage, which obviously, you know, you may not even be able to compute something like that with 3 bits, or you can actually compute something like this with quantum bits. But it's it is you have to take into account the whole thing, right? The whole process that you put in place. So
very cool. Any other questions? I saw other people log on. We have Claudia, Shahar, Kino, Paul, Ravi. So Ravi was at the big, it's called March Mingle in San Diego, 400 registered. So I had a table. I was one of the sponsors.
cool.
So Ravi stopped by in the beginning, at the end, and I finally got to meet him in person. Ron is a frequent. We've heard from Ron, Vijay, and Yusuf. If you have any questions, this is the highly technical stuff. There will be some stuff to feature David. You know, the more, I guess, less technical stuff is coming up too.
Yeah.
But yeah, feel free to raise your hand, and then you can continue, David.
Absolutely. Thank you. So as I said, you know, let's step away from the kind of the technical kind of world, and let's see what we really can do with quantum computing today. There's obviously a lot of myths out there that people think that you can do. You can break, as I said, you know, modern encryption methods in seconds. We cannot do it yet. Theoretically, we can do. It's not possible, and keep my fingers that hopefully cannot happen anytime soon, because we literally don't have a replacement for it. It would change everything, the way we live, if we could break it down. And reversing classical computers entirely, I don't think quantum computing will ever replace classical computers, just because, as I said, you only do processing with quantum computers. Everything else is done with classical 0 and 1. And communication, which is a big part of any computer network, is always done with 0 and 1. So what can we do really is, I think it's really creating attention is really creating a new way of thinking. And I think that was one of the reasons that I named the book Quantum Native. Really think about new methods of things that we can do. We've been doing some things with classical computers. Let's put that aside. Let's see what we can do now natively with quantum computers, and new problems that we have not even thought of so far, and which would be, again, a lot in the field of data science and machine learning, less and less in other areas, but there's still a lot of things that we can think of. And I have a whole map, you know, and what we really can do, there's obviously what we say quantum speed up, you know, that's faster processing is a big thing with quantum computing. And what we can do, obviously, is doing things faster, which enables us to come to a conclusion sooner, you know, finding soon. And when we talk about, like, for instance, stock trading, which every second counts, you can come up with much more capable platform to actually perform some kind of trading much faster. And but again, you know, you have to make sure that the answer that you have is the right answer, right? So we're talking about optimization, cost-effective routes for shipping goods. This is a very big thing. For telecommunication network, we're talking about, you know, a global network. What's the best route to route signals, you know, and this is a really big thing. And production line, yeah, obviously that's very important. And actually, I stop here because I want to go to another slide to discuss this in more details. And in almost every industry that we look at, I mean, obviously this is some classifications because of maybe industry sectors that I've been working. You can classify in different, you know, financial services, risk optimization and fraud detection is really, really big. And that goes into the machine learning area, where you can actually do this more effectively. And designing portfolios for you know, kind of thousands and maybe thousands and hundreds of thousands of assets that you can trade per second. You know, healthcare, obviously there's a lot of work done in drug discovery, and even like relevant to this, material science is also feeding a lot of that these days. that all of that impacts actually manufacturing. Manufacturing is one of the areas that is doing a lot of investments on quantum computing, more specifically automotive. And actually I'm linked to the automotive industry in Germany, where there is really a lot of work being done right now in this area. Not practically, but they're working on it. And there's even, online, in the internet, you can find some of the work that's been done. Energy and utilities, obviously, there's a lot of work in just energy itself, ways to distribute, ways to distract, all that stuff is areas that can be done. Cost saving, one of the areas that actually I thought maybe not even fitting here is global warming. People are thinking, what are the ways that we can actually tackle this, in terms of, that goes back into the healthcare, what are the best way that we can actually remove the CO2 from the environment. And media and technology, maybe not as much investment right away, but one of the areas in media and technologies is very important is data science, and looking at their viewership and things like that, what kind of products is suitable for a region, and that none of that is being done with quantum computing because the need is not there, but there is some investment happening. Yeah. I believe we discussed this a little bit, that, machine learning, and this is actually the map that I wanted to discuss, really, where various areas, in quantum chemistry, quantum simulations, various use cases coming together, and to essentially find use cases, right? And there, it's surprising sometimes how interlinked one application is to another, one use case is to another. They can actually use some algorithm with some changes in a completely different use case. Search algorithm, which is very, very effective with quantum computing. You can do this in, pattern matching, protein unfolding. You can do it, as I said, climate is actually one of the areas surprising that actually happening in quantum computing, in the field of chemistry in general, and in physics. And so these are the kind of the map that you can use in a way to kind of see where the use cases are going. And in all this, I think machine learning and in general data science, neural network has a really big chance of making a difference that would fall under, essentially this area. And where we are today is not where we're going to be. So there's been significant, it's actually shocking, how fast it's gone. If you think about classical computers, how long it took that we went from, like in the 70s, early 70s until we're today, like 4 or 5 decades, to where we are. But quantum computing has had a much faster growth, which says in the future is going to be a lot faster too. In a few years, we've been able to really provide it as in a way, a cloud platform for everyone to test quantum computing, which really wasn't the case for a long time for classical computing. And each provider is really trying to invest more qubits, less noise, and kind of a better software development kit that actually would enable testers to keep developing. And I think that's where we are at the phase that we constantly have to develop to different use cases, and to kind of constantly improve, and also going global. I see D-Wave actually every once in a while they announce a new region that they have opened up that you can run, which is very helpful. Also IBM, as the more they deploy, because if you actually run this and you have to wait in line, because obviously when I test, I use the free source, and when you use a free source, you have to wait in line until you have the qubit to run, and it can take a long time. Sometimes I remember once actually I ran it overnight, and in the morning it ran several hours that I was in line. So, but the more they add, so it kind of makes this time shorter and shorter, where you can actually, if you're writing a software that does testing, it does this testing much faster on the same platform. So a lot of really good things coming up definitely from major providers. And
so David, for annealing, it says 5 microseconds. What is that referring to?
It's annealing. I think it's the from the time you run. So when you from the time that you run on the quantum device until you have a response, there is essentially some kind of response time that you get, and you can wait in line for hours, but once you actually run it, the result comes in really fast sometimes. You know, it literally takes fast and it kind of gives you the output and you walk away, unless you have multiple jobs that's running. That's refers to that. But it's the per qubit, and this is also per qubit, right? So cool. Quantum computing advantages. Yeah. So as I said, you know, there's a lot of improvements are not only done on the hardware side, you know, and there's also on the software side. There's a lot of companies coming up with new APIs. As I said, you know, AWS API is really, really good. I like it because you can run multiple platforms. And this slide is actually a bit older. Before I was really working with AWS Bracket, I didn't update this. But if you think about that's the Ocean software kit from D-Wave, which is really, really good. And yeah, Google is actually expanding their software development kit. So the development is going into various domains. So we're talking about having more quantum bits. I think now it's 2048 is what Google provides, which is a lot, you know, compared to like 6 that's a few years ago. And we're talking about more quantum. We're talking about less noise. We're talking about a better way of interacting. Yeah. So in a few years, right now, if you want to do quantum computing, you still need to understand quantum mechanics, which is, I think, the biggest problem for a lot of developers. You know, I've worked with a lot of developers that they want to become quantum developer, and that's, I think, their biggest challenge, to really grasp the concept, especially if your background is not science. And there's a lot of learning tools out there. You know, MIT has a really good platform. IBM itself has a really good platform. I don't know if that can be that helpful. Obviously, these books that are out there, including the one I did, has provide some basic understanding. But again, you know, like when I was writing the book, I felt like, oh, I have a section about linear algebra. I wasn't planning on doing it, but as I was writing, I'm like, okay, maybe the reader doesn't know linear algebra, which is very important in understanding how these equations work. So, but maybe in a few years it's different. Maybe in a few years, the same way the cloud is today, you know, you don't have to know the backend to actually do this. You have essentially they provide an API for you that you can just test things without knowing the details. I hope that comes to that. So there's a significant amount of investment is being done in quantum computing, and I don't think there is an enterprise in financial sector, in manufacturing, big companies that they are not doing quantum. Everybody is doing. They have some activities going on, and because they see the kind of impact that it can have, and they should be ready for it. So it's important to have some plans and to have some skill set in the house or from consulting companies. And in the short term, really, it's important to really start learning. You know, as I said, you know, it's important to have some people dedicated to learning quantum mechanics and understanding of quantum computing. What area is important for that business is very important. You know, I think that's one of the areas that in conversations that I've had with customers is, what can I do with it? You know, and I said, I've had that conversation with like oil and gas, and in manufacturing, in a bank, it's very different conversation. How do I fix my problems with this is very important, and identifying those use cases and really going right away into testing, you know, how you can actually do this, I think is going to be really important. And in the long term, really important to have a roadmap. As I say later, really a quantum center of excellence is very important to have, and the kind of skill set that needs to be in that area is very important. And I was reading a report from, I actually have this next slide. I said, you know, may finish this, appoint employees, obviously, and quantum ready applications. And hardware agnostic. That hardware agnostic interface that I said that's what we talk about, that you'll be able to run on multiple platforms. It's very important. And if you look at this is one of the most recent reports from Gartner, from hype cycles for cloud computing. As I said, most of the time quantum is under cloud, and as you see, the expectations from quantum computing is very high, and the expectations are not right away. As you see, the most C-level, they have marked this 10+ years as far as the goal that they have. They have very high expectations. If you compare these to like cloud native, that that they have much shorter timeline that they want to get out of it, like edge computing and coming. But quantum computing, very high expectations, but much longer time scale. Most C-level, they have marked this. And in emerging technologies, again, this is from the same report from late last year, from the C-level of Fortune 500 companies. Quantum machine learning is actually marked as one of the areas that a lot of companies are looking into. Again, the timeline is longer for them, but nevertheless they're looking into, and there's investment going around it. So type of investments that's right now going in quantum computing is obviously is going to increase, but if you look at the kind of growth, the companies over 10 million a year investment is going to grow significantly in the next 1 to 2 years and 2 to 3 years. So we're talking more and more money coming in. This goes into recruiting people, qualified people, which creates job opportunities. This goes into program. This goes into actually partnership with the providers of quantum computing platforms and the cost. This goes into various areas, but that's kind of you see that investments for large investments is actually increasing in the next 3 years. This is a recent one from IDC actually. And this report is from last year. So when it says the next 12 months, these are actual numbers of the report from IDC. But as you see, the expectation is that after the next 3 years, the amount of investment in quantum computing is going to increase. More than the speed is going to be more. So there's going to be more and more money coming in this area in the next few years. So it's really good time. We're living in a really good time, except the war that's going on. But besides that, a really good time in terms of opportunities that this can bring for us, and we have time. That's one of the things that I like to show this curve to customers, is that we have time to prepare, but we need to prepare right now, because quantum computing, unlike cloud computing, is not going to be that easy to grasp. It's going to take time for your teams. It's going to take time. That short-term and long-term plan, it's going to take time to present. And in the next 5 to 10 years, there's going to be enough time to actually prepare, but you need to start right away. Yeah. So, and how I really envision this should be part of the CIO initiative, and it is. I think there was a report from Deloitte that I put in the book that shows it is one of the together with the digital twin. And artificial intelligence is one of the technologies that CIO initiatives, most companies, they have. And with respect to the areas that it can work and the providers, this is really should be the ecosystem of a quantum. I don't say should be, right? But that's what I've seen. This is based on experience that I've put it in here. It can be a very good starting point for a lot of companies to actually really get into the algorithms library, what kind of use cases you want to fix, bring in the different relevant teams, the cloud competency team, the DevOps, SRE people that actually need to be implementing some of the workload, identify those guys, and have a dedicated quantum competency program that involves the steps that we discussed, finding the right use cases, formulating the use cases, and really approaching this from various angles, and at the end is really to have that quantum native application, that can take input from the user, process it on multiple machines, and give you an output from various results. And that's something that We've done once, actually, to be honest, and it's very exciting when you see the output that you can really do it. It's really exciting. So an application, I think this I showed earlier, you know, can this is from 1QBit because the use case that we did was on 1QBit platform, but you can see that the stack, the application stack can have various ones. And in the book, I presented the application stack from several software development kits that it looks different, you know, like D-Wave has a very different kind of stack than, I think I included D-Wave and IBM. I don't remember which was the other one, but a couple of them I reviewed, and the stack can be different, and just because of the way it processes it, and so but you can have kind of APIs that kind of works with different platforms, right? So that kind of is the meat of the presentation. When we come to data science, 3 areas in machine learning we look for. One is really the reduced runtime, which is the speed up we get, and the reduced amount of training data, you know, training the algorithms and the data that we actually have to use for the model to come, and robustness, robustness to noise. That's kind of very important for a machine learning algorithms. These are metrics that we look into, and that's where quantum computing can really help. That's one of why I say, and it's very clear. And machine learning, we have reinforcement learning, unsupervised learning, and supervised learning. And what I see is the unsupervised learning as in one of the areas that can make a difference with respect to quantum computing. There is, in general, quantum machine learning has, I think, some kind of a grid where you say, okay, what kind of data I'm looking and how I'm processing it, what kind of algorithm. We have quantum data and also classical data where we actually have, and then we have type of algorithms. The sweet spot for quantum machine learning is in the CQ, where we used classical data, raw data, unstructured data, and we try to solve that with quantum algorithms, which this is the most common way, because most of the data out there is classical data. We don't have that much quantum data. It's classical data, and if we can fix that, we can kind of use that quantum computing to address that. I think it's where the biggest area is. And there's actually an article about this. I put the source here where I'm happy to put it in the chat, where the prediction is that quantum supremacy most likely will be done through the sampling, improving sampling with machine learning. That's where the prediction is, and there's significant work has been done and is being done. And obviously there's a lot of theory out there. I don't want to do too much theory, but what I'm working is obviously a lot of really applied way, you know, actually doing these things.